Homework 3, problem 10. Find the electrostatic potential energy for a spherical shell using these two formulas. The first one is essentially this QV formula that we had before, but now it's the integrated form. And the other one is kind of a neat little trick to turn this formula into a product of the electric fields. So let's go through each one. In part A, we need to write down what rho is. Rho for us is all on the surface. So this is going to be the surface density times delta of little r minus capital R, where that is a Dirac delta function. This should make sense because then if you integrate the integral d3x of rho of r over all space, you're going to get the integral 0 to 2 pi d phi, the integral 0 to pi of sine theta d theta, and then the integral from 0 to infinity of r prime squared dr prime sigma delta r prime minus capital R. This gives 4 pi. This evaluates this thing at capital R, so that's just capital R squared times sigma naught. And so it says that the total charge, because this is the total charge, is the surface area of a sphere times sigma naught. And so that's the charge density that we're going to want. The potential, because this is a spherically symmetric case, we know that the potential is going to be this total charge over 4 pi epsilon naught 1 over r. But the total charge, right, is this 4 pi r squared sigma. So this is 4 pi capital R squared sigma. 4 pi's are going to cancel. And this is going to be that the potential, in this case, is 1/2 the surface area times this. And so let's just write this down, not the potential, that Q EL is 1/2 the integral d3x of rho 4 pi capital R squared, rho sigma naught delta r minus capital R times V, which is capital R squared sigma naught over epsilon naught little r. This integral d3x is going to be 4 pi integral r squared dr. We're going to have a delta of little r minus capital R, and we're going to have a 1 over r, and then we still have the capital R squared sigma naught over epsilon naught. The integral of a delta function simply evaluates what's inside at that point. So what's inside is simply r, so this gives me another r. And this says that taking this up here, the electrostatic potential energy for this case is 2 pi r cubed sigma naught over epsilon naught. So that's for part A. In order to do part B, I need to find the electric field everywhere. But the electric field everywhere isn't going to be that hard to find. I know the electric field. I'm going to cheat a little. I know the electric field in spherically symmetric cases needs to be Q over 4 pi epsilon naught over r squared r hat. This is what the electric field is in spherically symmetric cases, where Q is the charge enclosed. For us, the electric field is going to be the charge enclosed. We've already done this. This is that 4 pi capital R squared sigma naught. And so the electric field is going to be equal to 0 if R is less than the radius, and is going to be equal to R squared sigma naught over epsilon naught R squared R hat. And this is for R greater than R prime. So now if we want to evaluate the integral, the electric field is equal to epsilon naught over 2, the integral d3x of this thing squared. And so this is just e squared. Let's replace this integral d3x. This is going to be a 4 pi and an integral of r squared dr, and then this thing squared. And so this is r squared sigma naught over epsilon naught little r squared, whole thing squared. This is going to be 2 pi epsilon naught r to the 4th sigma naught squared divided by epsilon naught squared. And then we have an integral here, and the integral is the integral of dr over r squared, and it's going to go from capital R to infinity, because it's 0 from 0 to capital R. So capital R to infinity. This integral, this little part right here, simply evaluates right to minus 1 over r, evaluated at infinity of capital R, which is of course simply positive 1 over r. So taking that all together, this electric field in this case is going to be 2 pi r cubed sigma naught squared over epsilon naught. And so let's compare that to what we had before. Let's see, before I should have had 2 sigma naughts, but I didn't. I missed the sigma naught squared part of things. So this is sigma naught squared, and now we match exactly in the two cases, which is what we want.